Hi everyone, and welcome to the first of 4 videos going through some past exam questions on the topic of the equilibrium constant, Kc. Now in this question, we've got our reversible reaction here, and it's asking us why is the equilibrium mixture both cooled and put under pressure. So here it's talking about changes to the conditions, so this is probably a question that involves applying Le Chatelier's principle. So if we cool the reaction down, according to Le Chatelier's principle, the position of equilibrium is going to shift to counteract this change. So it's going to shift in order to heat the reaction up again. If it's going to shift to heat things up, it means it's going to shift in the exothermic direction, because exothermic reactions are the ones that make things hotter. What's going on with our enthalpy change? We can see from here that delta H is negative, so that's telling us that it's exothermic in the forwards direction, going from left to right. So if we cool the reaction down, so if we say cooling the equilibrium mixture will shift the position of equilibrium, and because we already said that the forwards reaction is exothermic, cooling it is going to shift it in the exothermic direction, so it's going to shift the position of equilibrium to the right. So cooling the equilibrium mixture will shift the position of equilibrium to the right because the forwards reaction is exothermic. Okay, what about the change to the pressure? So if we put it under pressure, it means we're increasing the pressure. So according to Le Chatelier's principle, the equilibrium would shift in order to decrease the pressure to counteract this change. In order to decrease the temperature, we're going to shift to the side that's got fewest molecules of gas. The fewer molecules of gas you've got, the lower the pressure is going to be. You can see that we've got a total of 3 molecules of gas on the left-hand side, 2 of NO and 1 of O2, and we've only got 2 molecules on the right-hand side. So increasing the pressure would shift the equilibrium to the right, so that the pressure would then decrease again, and it's counteracted the change. Okay. So increasing the pressure will shift the position of equilibrium to the right, because the right-hand side has fewer molecules of gas. And that's going to get us our 3 marks. Okay, 1 mark for saying the forwards reaction is exothermic, so the explanation there. 1 mark for explaining the fact that the right-hand side has fewer molecules of gas. And then the 3rd mark is going to be for saying that both changes shift the equilibrium to the right, which is what we want to do. Okay, so that's why they've made these changes, because then you've shifted the equilibrium to the right and you can end up with a greater yield of the product that you're trying to make. Okay. This part B at the bottom here is asking us to construct equations for some of the reactions that are going on. And these are quite common questions, so asking you to write equations for things that you might not have come across before. So what's going on in stage 1? Now if we go back up here, stage 1 it's saying ammonia is heated with oxygen. So let's go for that. We've got ammonia is NH3, and it's heated with oxygen, O2. Heated with oxygen in the air to form nitrogen monoxide. So we know that NO is going to be the product. And that's all it says. Okay, so we've used all the information from the question. Looking at what we've got here though, we've got hydrogen as one of the in the reactants, and we've got no hydrogen in the product. So there needs to be another product containing hydrogen. It's very unlikely there's going to be hydrogen gas. Not many reactions make hydrogen gas. You've sort of got reactions of acids with metals, and there's not a lot else really. The logic here is, look, if the nitrogen is reacting with the oxygen to make NO, then the hydrogen is also going to react with the oxygen and it's going to make water. Most of these questions where they don't give you the other product, it's usually water. They don't get very imaginative. So it's worth having a guess at water if you've got no idea. But we need to balance this equation. We've got 3 hydrogens here and we've got 2 there. So to balance the hydrogens, we just swap the numbers over. So we're going to put a 2 in front of that one and a 3 in front of this one. That's now giving me 2 nitrogens on the left, so I needed 2 to get 2 nitrogens on the right. And then we have a total of 5 oxygens, so I'm going to need to go and put 2.5 in front of the oxygen there. Okay, and doing halves is absolutely fine. You could multiply this all by 2, so you end up with 4, 5, 4 and 6, that would also be fine. But you can just leave it as 2.5, that's not a problem. And then it's asking us for stage 3, so what does it say about stage 3? Nitrogen dioxide is reacted with water. Okay, nitrogen dioxide is reacted with water in a series of reactions to form nitric acid. Okay. The first of these reactions forms a mixture of nitric acid and nitrous acid. Okay, so that's the other product. Then it's a case of balancing it. I've got my 2 nitrogens here on this side, so I'm going to need 2 NO2. I've got 2 hydrogens and 2 hydrogens, and then I've got 5 oxygens, and I've got 4 and 5. Okay, so we're done. Okay. This question then continues, and this is the bit where we start talking about KC in a bit more detail. So it gives us a whole bunch of information here, but the first thing it asks us for is to write an expression for KC, for this equilibrium. Okay, and this then means we need to go back to the sheet we had at the start, and we need to look at what the equation is telling us. So here's our equation here. Equilibrium constant, remember, is always the products over the reactants. So we're going to have NO2 on the top. And remember, we need to use the square brackets to represent the concentration. And in the equation, you can see we've got 2 moles of NO2. So that means in the equilibrium constant expression, the concentration of NO2 needs to be squared. And then we're going to have the reactants on the bottom. So we've got 2 NO. So that means we need the concentration of NO squared. And then we've got just 1 mole of O2. So we just need to put the concentration of O2 to the power of 1. Okay. Then it's asking us to calculate the equilibrium constant, including the units. Okay, so for this, we're going to draw our ice table where we're going to go down through the stages. Okay, so again, we're going to get our reaction back, and we're just going to write this across the top. And then we're going to go through this ice table. So we're going to say how much do we have initially, what changes during the reaction, and how much do we have at equilibrium. And to find out the information for this, we're going to need to look at all the information that's up here in the question. Okay, so what's it telling us? It's telling us that we've mixed together 0.8 moles of NO. Okay, so that's what we had to start with, and 0.7 moles of O2 in a container with a volume of 2 decimeters cubed. Okay, I'm just going to put that to the side. We're going to need that later on. Heats the mixture and allows it to stand at constant temperature. Okay, so it comes to equilibrium. It's kept under pressure, so the total volume stays the same. That's good, so we don't need to worry about that changing. And at equilibrium, 75% of the NO has reacted. So if we've reacted 75% of it, it means we're going to have 25% left at equilibrium. So the equilibrium amount of NO is going to be 25% of 0.8. So that's going to be 0.2. So we've got a quarter of it left. And therefore the change that's happened is that we've used up 0.6 moles of the NO. Then we need to look at the ratio here. It's a 2-to-1 ratio. Okay, so that means if I'm using up 0.6 moles of the NO, I'm going to use up half as much of the O2 because they're going to react 2-to-1. So I'm going to use up 0.3 moles of the O2, and so 0.7 take away 0.3 is going to leave me with 0.4 moles. What's going on with the NO2 here? Well, it doesn't say anything about how much NO2 I had at the start, so we have to assume that we had no NO2 at the start. And then to work out the change, again, we're going to apply the ratio. Okay, we've got a 2-to-1-to-2 ratio, so the NO2 should change by the same amount as the NO. So the NO went down by 0.6. NO2 is the product, so it's going to be plus 0.6. And so we're going to end up with 0.6 moles at equilibrium. Now, we can't just take these numbers and put them into our KC expression because these square brackets represent concentration. these are not concentrations, they're numbers of moles. So we need to convert them into concentrations first. So I'll just add another row to the table here. How do we convert from moles into concentration? We need it in moles per decimeter cubed. So we need to divide by this volume that we noted at the side earlier on. So we just need to divide all of these by 2. Okay. So we can put this here and say we're dividing by 2 now. So again, that with 0.1. And this is now moles per decimeter cubed. And 0.2 and 0.3. These then are the equilibrium concentrations that we can put into this expression. So therefore Kc is going to be equal to, just stop and be careful here and make sure you get the right numbers in the right places. We want the NO2 on the top, so we want 0.3, and that needs to be squared. And then we want the NO squared, so we want 0.1 squared times 0.2 on the bottom. Okay, so let's just work that out. 0.3 squared is 0.09, 0.1 squared times 0.2. And we end up with a value of 45. Okay. Does that make sense? Well, Kc can be anything really. The value of 45 tells us that it's closer to the products than it is to the reactants. The position of equilibrium is shifted to the right. And if you look, well, it's not super obvious at equilibrium, okay, because we've got a total of 0.6 and a total of 0.6. But it is telling us that it shouldn't be a really, really tiny number. It shouldn't be a really, really big number because it looks like it's kind of similar. The fact that it doesn't come out as 1 is because some of these things are raised to higher powers than others. So if you're thinking, hang on, that adds up to 0.6, that adds up to 0.6, surely 0.6 divided by 0.6 should come out as 1. Well, remember, we're squaring some of these numbers, but not others, so that's why. Last thing we need to do is work out the units. So we just need to substitute the units into here. Okay. So we're going to have moles per decimeter cubed squared. We're putting moles per decimeter cubed in because these are all concentrations. And then on the bottom, we're going to have moles per decimeter cubed squared and moles per decimeter cubed. So these two that are squared can cancel out. And we're going to get 1 over moles per decimeter cubed. So that is equivalent to moles per decimeter cubed to the power of -1. And then we work these powers out. So it's going to be moles to the -1, decimeters to the +3. Okay, and then usually you write this with the positive power first, although you would get marks for that. But the proper way of writing it is to say decimeters cubed per mole.